Okay, in this video tutorial, I want to show you how to do a free vibration problem in the Catia program where initial displacement is specified. I'm assuming it's a single degree of freedom system, and therefore the series is called Flying a Fly with a Cannon. Because these type of problem are standard things in a vibrations calculation in a elementary vibrations book, and one does not need to use a powerful Catia program to do something like that. Here's a problem that we're going to do. We have a mass and a spring, and the properties are given here. The natural frequency of vibration of this is square root of k over m, which is 2 rad per second, and the natural period or period of vibration is roughly 3.14 seconds. Now, the initial conditions are given, so at time t equal to 0, this has been displaced by 1 millimeter or thousandths of a meter, and it's released from the rest condition. Elementary vibrations gives you a solution, analytical solution like that, but what we want to do is ask Catia to do this thing for us. The problem is that in Catia, dynamics is linear dynamics, and therefore the Duhamel integral or convolution integral in order to calculate is used in order to calculate the response. Now this F is the force acting on the mass during the time of simulation. The thing is that this is a free vibration problem. There is no force acting. So what we're going to do is to trick it here so that we apply a load, a force, which moves this thing to 0.001 slowly enough so that we have a force, and then once it reaches that position, then we're going to release it so F drops to 0, and this is how Catia is tricked to do a free vibration problem. So I'm going to do that. So do this thing for 3 force versus time curves. One of them is this stretching of the spring or the movement of the mass is over one natural period. So notice that here the force is 0.004 Newton because I took the displacement, which was 0.001, multiplied it by the stiffness of the spring, and I get that many newtons. Then I'm going to repeat this thing, one for 0.8 of the natural period, and then one for 0.5 of the natural period. You see that as this thing becomes faster, as this displacement to that final position of 1 millimeter is done over a shorter period of time, you will see that the numbers get worse and worse, because this has to be done in a very slow manner. And I will be using the rigid spring element, spring rigid element. There are other options. For example, you can also do rigid, spring rigid, etc. But this will do fine for single degree of freedom system, so we're going to use this. All right, so let's go ahead and get to our Catia program. I'm going to start a part file. There we are. And I create 2 dummy points where the spring essentially is going to be placed between those 2 points. Although springs don't have length, but just so that I can see things on the screen, I'm going to make them these 2 points 1 meter apart. The actual number is irrelevant. So I'm going to put a line between that point and this point. And because this is going to be meshed with beam element, and it has to be done, there is no other way, to the best of my knowledge, but you're not going to use this beam element, but in order to be able to specify the stiffness of the spring and things like that, you need to mesh this thing with the beam element. So or some element actually, it doesn't have to be beam, but this is a line, so we're going to use beam element. But before doing that, I'm going to put the material on a dummy material on it. Aluminum, double click on the aluminum here so that we change these things to such small numbers that they will not affect the stiffness and the mass of the spring, mass of the problem. So 0.1, this is 10 million times smaller, obviously. And for the density, I'm going to make it 0.1, which is 2,000 times smaller. So this is just putting some dummy material on this. Once we are done here, then we're going to go to generative structure analysis. And we're going to do a static analysis first, although we're interested in dynamic. We need to mesh this thing with beam elements. So I'm going to click on in the model manager on beam measure, select that. and I use a minimal mesh, that means that it doesn't matter what number I put here, minimal mesh is going to put a single element through that. I could have done this thing with 1 meter line and then uncheck that, but it doesn't matter really. And then I have, because we're using beam element, we need some properties here. So let's go ahead and apply 1D property. Again, these are dummies. So I'm going to put a circle, cylindrical beam, radius of 0.1 or 10 centimeter. But this is totally irrelevant. It's not going to be used, but you have to do that. There's no other way. Okay, so in fact, you can see the mesh if you want, right-click mesh visualization. And if you look at it, there's going to be a single element, right element, minimal mesh, right? One element going between nodes 2 and 1 here. Okay, so let me deactivate this. All right, let me hide these 2 points so that we don't inadvertently make a mistake here and put restraints on the nodes and things like that. I'm going to create a connection because I want my spring element going from this point to this point. So we create a connection, general analysis connection between this point and for the second component, that point. Okay. And this connection that we create right there, we're going to make this thing in that toolbar, distant connection property. There's something called user define distant connection property. You click on it. For the support, you select the connection. You have to select the connection right there. See that? And it's going to be spring rigid. You click on the wrench and you put the stiffness in the y direction of 4 newtons per meter, and that's it. Good. Now, I think I mentioned to you that we're going to do a static analysis first, right? So we're going to put this thing is going to be clamped. This endpoint is going to be clamped, and this other point is going to be free to move along the y direction, because after all, this will be vibrating along the y direction. Everything else is fixed. Good. Now let's put a force here of 1 Newton and 1 Newton. So if you put a force of 1 Newton here, a dummy force of 1 Newton, here is a load. At this point, we put in the direction y 1 Newton. Now, if I run this thing, nothing fancy is going to happen. This is going to stretch, and the value of the stretching is going to be 1 Newton divided by the stiffness of that spring, which is going to be 0.25 meter. Okay. Now remember, we made the stiffness of this beam so small and the mass of it so small that basically they will not influence anything dealing with the spring. So let's run this thing, make sure we get 0.25 so that there are no mistakes when we do the rest of the problem. Okay, good. So look at the deflection, 0.25 meter. Good, nothing exciting. So deactivate this plot. Deactivate that. All right. Now we're going to insert a frequency case. And for restraint, we're going to use the stuff that we already used. See under reference, you select the restraint, use the same restraint. And by the way, when you do that, if you check this thing, it's going to double click on that line. It's going to try to extract 10 frequencies. But this is only single degree of freedom system. I can leave 10, and when I run it, it's going to come back and complain that I don't even have 10 frequencies. So let's do it 1 now. Remember, if you leave it anything beyond 1, it's going to come back and say there are not that many frequencies. So change this thing to 1 so that we don't get that error message. And just run it. Nothing exciting is going to happen. It's going to just give you the frequencies right there. And if you double click on this, it gives you, oh, you know what? I forgot to put the mass there. Oops. There's a mass. I completely forgot. Okay, so forget about that. Let's leave it. Let's go ahead and apply the mass right there. Masses, distributed mass right there. You select that point and you put a mass of 1 kilogram. That's the thing that I forgot. And run it again. I better get 0.37 hertz or something like that. I double click on this, 0.318 hertz, which is right here, 0.318 hertz. Good. Now that we have that, we wanna go and do insert a transient dynamic response. You click on it, and for the frequency, we're going to use for the thing that we already did right there, and we say OK. A couple of things here. First of all, if you double click on this line, it says what is the duration of the maximum, what's the duration of simulation? Let's put 10 for now, it doesn't matter. Okay, and we're going to have to come back and change this thing from 20 steps to 200 steps or something, because 20 is going to be very choppy. You'll see that. Let's not leave it the way it is right now. Now, as far as damping is concerned, double click on it, click on the range, automatically it puts 1% damping. So let's make that thing 0 if it's an undamped problem. Good. Very good. Now, if you double click on load excitation, it says where is the load? The load is that static load that we applied, which is oops, not there. Static load right there. And then it asks us for modulation. What is the modulation? Now the modulation means exactly this graph. So I have already created Excel spreadsheets with this. Okay. I can show you what it is, but really, basically, it's an Excel spreadsheet giving this data 0, 0 to a Tn and this value, and then drop to 0, and then 0 all the way to the end. So I'm going to import all three modulations because it's asking for it right now. See, it says where is it? Well, I don't have it, so cancel that. Now here is the situation. This is under modulation, and it's a transient time modulation that we want. You click on it and browse. It says where is it? It's right here. I have 3 of them. So there is the first one is 1 TN right there. Okay, let me change this thing is 1 TN. Okay, just so that the name you recognize. Right there, you can see that under modulation. Somewhere here. It says 1 TN. And do another one. We're going to do 0.8 TN. 0.8 TN. Browse. And that's this one. Okay, so there is the other one, 0.8 TN. Too many P's here. So let me change that thing, 0.8 TN. Another one. You don't have to do all 3 of them. It's just that I don't want to do this thing every time, so I'll just import it all 3 of them at the same time and then use it as needed. This is 0.5 TN. 0.5 TN. You just need 1 of them, right? Okay, all 3 of them are here at our disposal. Now we go there. Double click on double click on load excitation. For the load, we're going to select that load from the tree, the static load. And for modulation, select the modulation. Let's go select the first one. This is 1 TN, okay? And then we say okay. Yep, that's pretty much it. We don't have to run anything. Everything, this is a linear dynamics problem. You have an integral. The only thing that's needed really is that frequency that was already extracted. The rest is just post-processing. So if you right-click here, oh, by the way, before I do that, let me put the cursor, put the cursor here, right-click 2D display, generate 2D display, and this is the first one. Notice that it goes between 0 and 3.14. Let me close that. If you want to do the other one, right-click, a 2D display. This goes between 0 and 0.8 TN, etc. This is just so that you can see it. You don't have to actually create these things. So let's go here. Double click on it. We agreed that we're going to go up to 10 seconds, 20 number of steps, but this will make it very choppy, so just leave it the way it is. You put the cursor here, right click, generate 2D display. Next, one graph, finish. It says, okay, where is that node that you want to plot something about? So we minimize this. We go back to our analysis right there, and we are trying to pick this node. Now, you can't pick it from here. So what we do, we hide a bunch of things, hide, still can't pick it, hide, and now we can pick it. There. And this is node number 1. We say okay. And notice that the plot has been generated here. And this was for TN, 1 TN duration. And there we are. Now, a couple of things. Notice that, first of all, this is very choppy. So I'm going to close this. I'm going to close that. Go back to the transient dynamics. Instead of 10 or 20, I use 200. Okay. Now, double click on this thing again. And there we are. It's not choppy anymore. Now, the other thing I want to do is that this is the amplitude. If you want positive or negative values, put the cursor on this amplitude, right-click format, real. And there we are. So notice what happens is that the force has been applied over one period, which is roughly 0.314, and it takes you to this value. And that is 1 millimeter displacement. You can see that slowly applied, the force is slowly applied, so that slowly takes it to that initial condition that I want, 1 millimeter or 0.01. And then after that, it oscillates back and forth, and that's exactly what this is saying right there. Okay, so now we're going to do this. We're going to close out. And for this time, we're going to use the other modulation period. So if you double click on load excitation, for modulation, we don't use 1T, we use 0.8T. Okay, 0.8T. And then we say okay. And then we're going to go and double click on this. Let's make sure this is right. Let me close that. Let me do another one. Select that point. That is still giving me the same curve. So let me see now. This still goes to point, still taking 1T. So I don't want that. Let me do the following. Let me close this. And let me actually delete both of these. Let's try this. By the way, I want to make sure that I did select the correct, 0.8 TN. That's good. That's good. So right click, generate 2D display. Next, finish. Let's go get it from the tree. Not from the tree, from the screen. This point. Add. And we say okay. And let's check it out. Oh yeah, 0.8. Actually, right there. You can see that 0.8 TN is right there. Say okay. Let's change this thing to real. Yeah. So it goes up to 0.8 TN is about here. So goes slowly to that. We can see that. It's a little bit bigger than, it's different from 0.001 meter, 1 millimeter, but you can see it affects it. Now, what I'm going to do is I'm going to actually I'm not going to delete these either. I'm going to go to here. Let's see if this thing works. For modulation, we're going to select this one, which is 0.5 TN. Let's go here, see what happened, but it actually did it for us. It looks like it doesn't. Yeah, right here, 0.5 TN. I double, in the last case, I deleted it and did it again, but it was not necessary. You can see that it's updated. So 0.5 TN is about 1 point something, 1.8, 0.5 TN. Let's see, 0.5, 1.6, 1.7. So gradually it's raising to that 1 millimeter over 1.6, 1.7. But you can see these numbers are not as good as before. Actually, let me do the following. Let me delete this again. Right click, generate, next, finish. Get it from the screen, that one. Yeah, that was correct. But the moral of the story is that the faster that thing is, where is this thing? Let me just get that for a second. The faster this thing is, the worse it's going to get. Okay, so this is about 1.6, 1.7. These numbers are changing more now. So the moral of the story is that if you make this thing rise to that final value very fast, the numbers are going to deteriorate. If you do it slowly, TN, 0.8 TN, 0.9 TN, 2 TN, 3 TN, etc., things are going to look a lot better. Yeah, I'm sorry about this deleting and doing it again. It was better if I deleted those, although it does update, but I don't know, something didn't work out quite right.